Hello everybody, and welcome to the Module 11 video for Introduction to Logic. Today we will be learning the method of existential conditionals. And what the method of existential conditionals it is our validity test for Boolean statement schemata. Okay, so the meat of the method of existential conditionals consists in these 5 laws concerning validity in Boolean schemata of various sorts. So first, I'm going to go through those 5 laws, right? Then I'm going to give you a precise statement of the method of existential conditionals, and then I'm going to go through a few examples. Okay? And so just so you understand what's going on when I'm going through the laws is the laws that I'm going to give you suffice for testing any Boolean statement schemata for validity, but they might not seem like they suffice at first. And so what we're going to do to make these laws work for any Boolean statement schema is we're going to convert the Boolean statement schema into conjunctive normal form. So the reason why you had to learn conjunctive normal form is so that you can kind of beat your schemata into a form where one of these 5 laws applies, and then we just use the relevant law to test for validity. So I'm going to urge you right now, if you don't have a good grasp on conjunctive normal form, like you bombed the quiz, you don't think you knew how to do the homework, please go back and practice that. I posted a video with some more examples where I annotate the equivalency rules that I'm using. Watch the original video again. If you know the definitions of the different types of Boolean schemata and you know how to convert into conjunctive normal form, at least easy-ish examples into conjunctive normal form, as you'll see in the video I posted, some of them can be really painful, right? This isn't that bad. It's in fact pretty easy, but if you don't know those things, it's going to seem completely impossible. So please, I'm imploring you, if you don't feel like you have a good grasp of conjunctive normal form, please go back and practice some more. Pretty please. Okay, so I'm just going to launch right into the laws. Again, what these laws will do is once we've transformed our Boolean statement schema into conjunctive normal form, and that's pretty easy. I'll show you what it looks like. It's not as daunting as it might seem. One of these 5 laws will definitely apply. I promise. So first law, right? And these are laws that concern Boolean existence schemata and Boolean statement schemata. So pay attention to which one I'm referring to here. So a Boolean existence schemata, right? Law 1. A Boolean existence schemata is valid if and only if its term schema is valid, right? So remember, just to refresh your memory, a Boolean existence schema is something like this. And it's a Boolean existence schema because it is a backwards E, which does not have a negation sign in front of it, followed by a Boolean term schema. And a Boolean term schema is just what we get if we take a good old-fashioned truth functional schema and make all the letters capital letters. So this is a Boolean existence schema, and it's valid because the term schema is valid. And so to test this for validity, what we would do is we would subject the term schema to truth value analysis. Like so. And it's valid, okay? So if you ever have a single Boolean existence schema and you want to test it for validity, that's all you need to do. Just one more example so you know what I'm talking about. So if we have, this, we would test the Boolean term schema inside of this Boolean existence schema, which is this. This is the thing I underlined there is the term schema for validity, with truth value analysis. And I'm going to use fell swoop. Right, so this is also valid. Okay, really simple. This one applies to just Boolean existence schemata that are by themselves. Not painful. Okay, so law 2 states that the negation of a Boolean existence schema is valid if and only if its term schema is inconsistent, right? So this one applies to Boolean existence schemata with a negation sign in front of them. So if we wanted to know whether or not this Boolean existence schema, or sorry, the whole thing's a Boolean statement schema because it has the negation sign right there. So if we wanted to know whether or not this was the negation of it was valid, we just test the term schema, and if the term schema always comes out false under truth value analysis, then the whole thing, including this negation sign, so the negation of this Boolean existence schema is going to be valid. So right, our truth value analysis always ends in false. And so we know that the term schema of this Boolean existence schema is inconsistent. And because the term schema of this Boolean existence schema is inconsistent, the negation of this Boolean existence schema, the whole thing, is valid, right? Yeah. This one's also not that bad. So if you run into a single negated Boolean existence schema, all you do is you test the Boolean term schema of that existence schema, so the P and not P, using truth value analysis. And if it always comes out false, then you know that the negation of that is always going to come out true, and it is valid, right? And again, so here, we could read this as there's not anything that is both a pi and not a pi. If we put in x is a pi for the p's here, and it should make sense that that's valid, right? I'm not a pi, and you are not a pi, right? So we can't be both pies and not pies at the same time. Nothing can be both a pi and not a pi at the same time. And because of that fact, right, there's no object that P can be both true of and false of, whatever we put in for P. Right. So if we were to say that, it's not, there doesn't exist anything that is both a pi and not a pi, the same thing, we said something true. Okay. Not a very complicated law. So the next one's a little tricky, and you need to pay attention to how this works. So the next law is if we have an alternation of negations of Boolean existence schemata, if we have that, it's valid if and only if one of those negations meets the above validity test. Okay, so let's look at an alternation of negations of Boolean existence schemata, right? So an alternation of negations, so we want something like not P or not. And I'm just using simple ones, so you should be able to see how this works. So what we do here is we have to test each of the, actually, I'm going to change this letter just to make it clear what's going on. Right, so we have to test each of the term schema in each of the negations of Boolean existence schemata. So first we do a truth value analysis for Q, right? Well, that was fast. And actually this, you know, you don't need to do a truth value analysis for single letters. I know how single letters work. So next we need to do a truth value analysis for this. It's basically what we just did above, but I'll do it again. Okay, so what this says is if we have an alternation of negations, we have to do a truth value analysis on each of them. And if at least one of them, remember they have to be negations of Boolean existence schemata, if at least one of them comes out inconsistent like this one here does, right, then the whole thing is going to be valid. And that should make some sense, based on what you know about truth value analysis, right? If we have, false or true, as long as one part of an alternation comes out true, we reduce the whole thing to true in truth value analysis. So as long as one of our negations of Boolean existence schemata in an alternation, comes out true, and it'll come out true, or it'll come out valid if the term schema is inconsistent like this, right? Then we know that the whole alternation has to always come out true. I feel like when I'm saying this, it doesn't make sense, but if you look at it, it should, right? And so you might wonder why we don't have, because I'm just going to spoiler, we don't have a rule for non-negated alternations. So what if we have an alternation of non-negated Boolean existence schemata? So let's pretend that we have something like, I don't know, something like this. So this is an alternation, right? You see the ors let us know it's an alternation, and it's an alternation of non-negated Boolean existence schemata. Again, they're Boolean existence schemata because there's a backwards E followed by a normal truth functional schemata except with capital letters instead of lowercase ones. And so if we have something like this, we don't have a law that applies to it, but this is where you need to remember that that E distributes, or the backwards E distributes over alternation, right? And if you keep that in mind, what we can do is we can factor out the E. So this is equal to this. Right? And so if we have this, we don't have an alternation of non-negated Boolean existence schemata anymore. We just have a single Boolean existence schema. And so if we wanted to test this for validity, we'd factor out the backwards E, turn it into this. And if we wanted to test this for validity, we just need our first law. A Boolean existence schema is valid if and only if its term schema is valid. So here we have a single Boolean existence schema. So if we wanted to test it for validity, we would just do a truth value analysis on its term schema, which is this. I don't have a space because I pre-wrote all the rules, so I'm not going to do that. But if you really want to, is that valid? I don't think that's valid. Oh, no. It is valid, I think. You can test it. I'm pretty sure it's valid. Anyway. Okay. Again, keep that in mind, this distributivity law where we factor out the E, because that's something you'll have to do to apply this method. And remember, it doesn't apply to negated. We can't factor out a negated backwards E. So we can't, we can't factor that out or distribute that. And that's why we need this law for alternations of negations, right? And all we do there, we test each component term schema for inconsistency in accordance with law 2, like this. And if the term schema of a negated Boolean existence schema always comes out inconsistent, like here, then we know that the alternation as a whole is valid. Okay? Cool. So again, not terribly difficult. Once you see all this together, you'll see that it's not as scary as it sounds. So the next law that we have is for existential conditionals. So I need to define an existential conditional. Actually, I forgot to write that. So an existential conditional is a conditional where the antecedent is either a single Boolean existence schema or a conjunction of Boolean existence schemata and the consequent is a single Boolean existence schema. Okay, I need to move this around. And again, this is one of those things that seems more confusing than it is until you see an example. Let me stash this down here. Okay, so here are some examples of things that are Boolean or existential conditionals. So okay. So again, the definition of an existential conditional, a conditional where the antecedent is either a single Boolean existence schema or a conjunction of Boolean existence schemata, and the consequent is a single Boolean existence schema. So if we look at A right here, so, the whole thing is a conditional, right? See, the antecedent is a single Boolean existence schema, and the consequent is a single Boolean existence schema. So it's an existential conditional. For B, right, the whole thing's a conditional. That arrow shows us that. The antecedent is a conjunction of Boolean existence schemata. Right, it's a conjunction of two things, and each of the two things is a backwards E followed by a Boolean term schema, right? And the consequent is a single Boolean existence schema. For this last one, then same thing. The whole thing is a conditional. The antecedent is a conjunction of Boolean existence schemata, and the consequent is a single Boolean existence schema. So these are all existential conditionals. And our law for existential conditionals asserts that an existential conditional is valid if and only if the Boolean term schema in one of the Boolean existence schemata in the antecedent implies the Boolean term schema in the Boolean existence schema in the consequent. Okay, and so I'm going to run out of space. So let me just show you what that means, right? So for each of these examples. So for A is pretty straightforward. So to test A, to see whether or not A is valid, this one, all we would need to do is see if the term schema in one of the Boolean existence schemata in the antecedent implies the Boolean term schema in the Boolean existence schema in the consequent. It's a mouthful, but it's really not as bad as it sounds. So for A, in order to test A for validity, we would just see whether or not this comes out valid under truth value analysis. Spoiler, does. Right, so A is valid, and that's all we need to do for A. B, a little more tricky because we have these conjunction of two Boolean existence schemata in the antecedent. And so we have to test each of them individually. So remember, in existential conditionals, the antecedent is either going to be a single Boolean existence schema or a conjunction of Boolean existence schemata. And what that means is that we have to test, for B, we need to do two different truth value analyses. So we'd have to do, again, just look at B. So that's a really ugly R. Right, P or so that's one of the things we have to test, and the other one is right. And if at least one of these comes out valid under truth value analysis, at least one of these two conditionals, then the whole existential conditional is going to be valid. This will not come out valid. I don't have space to do the truth value analysis, but I promise that it won't. So this, however, I have space to do. So this one, if we want to see whether or not this implies this, right? We set up the conditional like that and do a truth value analysis. So this does come out valid, and because the Boolean term schema in one of the Boolean existence schemata in the antecedent implies the Boolean term schema in the consequent, this one's also valid. Okay, so for this last example, what we'd have to do to see whether or not the existential conditional as a whole is valid is test three of these. So we'd have to see whether or not the term schema in this implies the term schema in the consequent, whether or not the term schema in this implies the term schema in the consequent, or whether or not the term schema in this implies the term schema in the consequent. So we'd have to do three at most truth value analyses of conditionals. So we'd get that's the first one we'd have to do, right? The second one is right, and the third one is right. Okay, and one second. Yeah, I'm pretty sure. Again, I don't have space to do all the truth value analyses on these, but I'm pretty sure that none of these are going to come out valid, and so C is not. The whole existential conditional in C, I'm pretty sure, is not valid. You can check if you don't believe me. I've done a bunch of these, and I have a pretty good sense of how it works, though. Okay? And so that's how existential conditionals work. This is probably the most confusing one, so pay attention. If you have any questions about this, please let me know as soon as possible. Okay, so the last example is, or the last law is really simple. It's that a conjunction of Boolean statement schemata of any of the previous forms covered in 1 through 4 is valid if and only if each of them comes out valid under tests 1 through 4. So if we had, say, or wait. Right. So what we'd have to do for this one is, so this whole thing's a conjunction of Boolean statement schemata. And we'd have to go through and do first here, we'd have to use our second law. The negation of a Boolean existence schema is valid if and only if its term schema is inconsistent. So we would test, P and not P for inconsistency. I've done this like 3 times in this video, but what's one more time? So, right. So, okay, our first part of the component of the conjunction, right, is going to come out. So this is valid under using the second law. The second one, we need to use our law for existential conditionals, and this is a simple one, so all we need to do is test, with truth value analysis. And again, I just did this, but to really drive home that at the end of the day, this is mostly just truth value analysis. And okay, well, our existential conditional there is valid. So by the fourth law, that comes out valid. So then this last one, right, I'm not going to do the full truth value analysis, but remember our third law, an alternation of negations of Boolean existence schemata is valid if and only if one of those negations meets the above validity test. Well, so this is one of the negations that's in this alternation of negated Boolean existence schemata. And we already know, because we just did the truth value analysis, that it is the term scheme is going to be inconsistent. So the negation is going to be valid. So, ta-da! And those are our laws. That's really all you need to test all of these. If I were a jerk, and Quine's kind of a jerk, so this is more or less what he does, I could just stop here and be like, that's the method of existential conditionals. Go do some practice problems. But so what I'm going to do is I'm going to formulate the steps for applying this precisely, but you have to understand all of these laws, because the method is just conversion to conjunctive normal form and then applying these laws. So if you're confused about any of these, you don't understand what I'm saying, double check. Like, you should write down the definitions of Boolean term schemata, Boolean existence schemata, Boolean statement schemata, because if you know the difference between those two things and you can recognize when you have a conjunction of, Boolean statement schemata or whatever, this isn't that bad. So if this has completely confused you, you probably don't have a solid grasp on the definitions of those. So please review the previous module. So what I'm going to do next is I'm going to give you the precise statement of the method. more or less. There's a sheet that I'm going to hand out that's in the book that has like the very long, precise statement of the method, but it's like a page long in 10-point font or whatever, because I have a bunch of examples. So I'm going to give you a precise statement of the method, or as precise as I can in the context of a video, and work through a few examples to show you that this isn't that bad. Okay. So I'm going to give you an introductory example that starts from the English, even though I'm not having you guys translate these yet, just to show you that we can translate a wide variety of English sentences into our Boolean schemata. So consider the argument, and again, this is silly, it's from the book, but I like silly arguments. Everything that exists, so first premise, everything that exists is a delicious apple pie. Second premise, some pastries are pies and some pastries are cakes. And the conclusion is that some pastries are delicious. And so if we were to translate this, putting in P for pie, D for delicious, S for pastries, C for cakes, oh, and A for apple. Forgot that one. This is what we would get if we translate that into Boolean statement schemata. Okay, so I'm just going to walk through how we would do this. So the first thing that we do is I'm going to set this up to see whether or not the premises imply the conclusion. I'm going to set this up as a conditional. So that gives us not. And remember, to do that, we just make a conjunction with all of the premises. And then we connect that to the conclusion with a conditional arrow. And technically that dot isn't necessary right there. Okay, so the first step, when we have something like this, we can't apply unrear test to this. This isn't an existential conditional. None of the laws that I just explained apply to this. So what we have to do is step one of our method of existential conditionals is to convert to CNF. Right, and so we convert, technically speaking, we convert the Boolean statement schema to CNF, and I have no idea how to explain this in a way that's confusing if you just listen, but here's how we do it. Pay attention. It's not that bad. So here, we're going to take this, and that goes to not P. So there's a negation sign in front of this backwards E here. And so because of that, we have to make sure that our P here is negated. Then we're going to take this to, actually, wait. I'm just going to group both of these because that's how it was originally, even though we don't have to. Anyway, so we're going to take this to Q, right? And then we're going to take this to R, and that gives us P, Q. This is just a shorthand. You'll go insane if you have to rewrite all of these. So what I'm going to do is I'm going to substitute in good old-fashioned truth functional schemata for the Boolean statement schemata, right? The whole thing here, and then I'm going to convert this into conjunctive normal form, and then I'm going to plug back in the Boolean schemata. So how that goes is this is a pretty easy conversion to CNF. So here, let me move it around so I have a little more space. Where to put it? Okay. So zoom in. So to convert this into CNF, this is, I don't have the rule sheet in front of me. I think this is rule 3. From our equivalency rules. right? Then De Morgan's, so, oops. Right, and then get rid of the double negations. Right. Oh, I did it in the book differently. I'm gonna back up and redo this exactly the way I did it in the book, even though it doesn't make that much of a difference. The way I did it in the book, I just want, in case one of you gets confused and wants to go look at it. So I'm gonna put that to Q and that to R and that to S. It doesn't really make that much of a difference. I'll erase that for space. So the first thing we do is convert to conjunctive normal form like this. We just keep track of the negation signs. So we have P, Q, R, S, and then same thing that I was doing, so not. That's just De Morgan's, then. Okay, and so this is in, well, it's in conjunctive normal form. And so what we need to do when we have something like this, where it turns into an alternation that's a mixture of negated and non-negated single letters that stand in for Boolean existence schemata, is what we're going to want to do just to start is we want to rearrange this using commutativity, so we get all of the negated letters, or oops, that's not negated, on the left. Q or not R, P or S. Okay, so now that we've converted this into conjunctive normal form and we've arranged it like that, what we're going to do is we're going to plug back in our Boolean existence schemata. And remember, so here, this is so this goes to Q, but Q's negated here, so we have to remember to negate it when we plug it back in. So this gives us one second. And then so this P here was negated originally, but when we transformed it into CNF, it's not. So we remember not to put a negation sign back in there. And then S is just. Okay. So what do we do here? Well, what we need to do here, and this is why you need to learn all those equivalency laws, is we need to do two things. So first, I'm going to take these and factor out the backwards E, because remember it distributes, like I said. So this turns into E. Give me 1 second. I think we need that. And damn parentheses. And then, okay, so that's the left side here. And then what we need to do here, and again, this is a little tricky because maybe you haven't been using De Morgan's law in this direction. So what we need to do is we need to factor out the negation signs using De Morgan's law. And we can do that. That's fine. We could do some of these steps with the substitution still in. I'm just doing this to be clear. So what this turns into is not right. So so then what we need to do with this whole thing is use our equivalency law for eliminating conditionals in reverse. So see, this has the form of, right, so, and we want it to be. So what we're going to do is we drop the negation sign from the left-hand component of the alternation. So that gives us and then to okay, and so now we have an existential conditional. And again, all we did to get that was we converted our original Boolean statement schema to conjunctive normal form. We grouped the negated and the non-negated components. We factored the backwards E out of the non-negated components of our alternation. And then we used De Morgan's law to turn this alternation of negated Boolean existence schema into just a negation of a conjunction of them. And then we used our equivalency law for eliminating conditionals in reverse to turn this into an existential conditional. Okay, I know this seems daunting, but it's really not too bad after you've done one or two and get the idea behind it down. And once you see the instructions on the rule sheet, it's pretty precise. Okay, so this is an existential conditional. And if we remember, in order to test an existential conditional for validity, what we've got to do is we've got to test whether or not each of the term schema, whether any of the term schemata inside the Boolean existence schemata in the antecedent implies this. So we need to do two different truth value analyses. So we do So that's the first truth value analysis we have to do. And the second one is okay. Let's see if I have space to do these here. I might run out of space. So let me zoom in really hard. Oh, actually, don't need to branch. So we can use fell swoop on both of these. So we are going to set for this side P and S both equal to true. So that gives us that's okay. And now we're just reducing, and I'm going to skip some steps because I hope that you can follow along. If I do that, so that gives us right, and then we branch on the D, so not. So that just goes to true. So this is going to be not false, which is true. And so we can stop here, actually. I think I did it in a different order in the book, so you actually have to do both. So because our truth value analysis for whether or not any one of the term schema in the antecedent implies the term schema in the consequent, if at least one of them ends up valid, so here this is one of the term schemata from the antecedent, comes out valid, then the existential conditional as a whole is valid. We don't even need to bother with this, right? So that's a quick sort of top to bottom example of how this works. So I'm going to go through a few more examples. And again, these are going to be in an argument form, but just to, remind you. So the method has 2 steps. We convert our Boolean statement schema to CNF. Then kind of as an intermediary, we group negations and non-negations. We factor out the backwards E from non-negations. And we use De Morgan's law to factor out the negation sign from negations. Then what we do is we create a conditional using our equivalency law. And the law is and then step 2, we use our Boolean laws to test. Okay, and this is how it works. So for some of them, you won't actually need to do all of the steps in step 1 because if you might convert to conjunctive normal form and you don't get any negated Boolean existence schemata, or it might just be a conjunction of non-negated or negated ones, right? So this is kind of the most you'll have to do. So let's just work through a few more examples of these. So the first example, I'm going to give these to you as arguments, is okay. And so, again, we should know by now that if we want to represent this argument using a conditional to test and see whether or not the premises imply the conclusion, what we do is, did I write that right? Yeah. Okay, so again, we do that trick where we just substitute in, and remember this has to be a not P because there's this negation sign here. This has to be a not Q, right, because of this negation sign here. And if we run into, like if we had, never mind, it doesn't really matter. And this has to be a not R because of the negation sign. So that gives us the conditional not P, not Q, R, right? And then what that does, if we convert this to conjunctive normal form, and a lot of these will look really similar, is that gives us R, and then we just De Morgan's this again, so that gives us and double negations cancel out. And then we rearrange this using commutativity to get the negations on the left side. So that gives us not R or P or Q, right? And again, we can do some of the steps in this shorthand notation where we substitute in the letters. So I'm just going to turn that into R, therefore P or Q. Okay, so that's the conversion to CNF. Again, these are not super ultra. I check to make sure they're not really hard to convert to CNF before I give them to you. Okay, so if we plug this back in, we get, and remember, if we lose the negation sign in the conversion to CNF, we don't put it back in. So this would be, remember to keep track of your dots. I'm just doing this for emphasis. And again, remember the negation signs. If they go away during the conversion, we don't put them back in. And so the last thing we have to do to prepare for our truth value analysis is we factor out, we reverse distribute, I guess, these over alternation, because we don't have a law that deals with alternations of non-negated Boolean existence schemata. So that gives us okay. And then to test this for validity, we just test whether or not the term schema in the antecedent implies the term schema in the consequent, right? And so what we just do a truth value analysis. And again, fell swoop, so applies here. Might even, never mind, I don't want to think about that too much. So that's true or, okay. So again, skipping a bunch of steps, we get, okay, so this is supposed to be valid in the book, but I forgot that there was a negation sign over one of the B's. Oops. Or wait, did I? Yeah, no, I just didn't write it in even in the beginning. Okay, anyway, we're going to see that this is not valid even though it was supposed to be. So, okay, so if I would have remembered to put a negation sign over one of these B's, it would have ended up valid, but I dropped one in writing it down. So because this comes out false here, and because we don't have any other term schemata in the antecedent except for that one, this is not valid. It would be if there was a negation sign there, but it's not. So on one, I guess, key advantage of the method of existential conditionals over methods that are taught in other courses is other methods only allow you to positively prove that schemata that actually are valid. So if I had made a mistake like that in a different way of teaching logic, you would have never, ever been able to figure out that I made a mistake. You would have just smashed your head against the problem for hours. It's one of the reasons why I teach this, even though it's a little cumbersome with all the definitions. Okay, so I'm going to just another example. So example 2, and again, just giving these to you in argument, premise, conclusion form. I'm going to try to not drop a negation sign here. Let me zoom in on the examples I've written down. I can't see the negation signs that well. Okay, so for the first premise, let's do and this is going to be a one premise argument, and the conclusion is again, there's no point in even trying to say this stuff out loud. So what do we do? Well, we make our conditional. We represent the argument as a conditional, so that I'm just gonna abbreviate that. Oh, and that should be a negation sign there. It's hard to see. Oh well. Okay. And so then we substitute in and convert to conjunctive normal form. So this is going to go to not P. Then this is going to go to not Q. And the conversion to conjunctive normal form is right, we just use our equivalency law and drop the double negation. Then we put our Q on the left. Right, then we substitute our stuff back in. I forgot what P was. Okay, so we get, so not Q, right? That's sorry, I was just double checking to make sure that I didn't drop a negation sign again. And then this monster of a schema. Okay. Oh wait, that's not negated. Sorry, my bad. See, it's easy to make mistakes where you add or drop a negation sign. That's why you don't lose too many points for them. Okay, then we turn this into an existential conditional using the same law that we just used in the other direction. So that turns into okay, then we see whether or not this term schema in the antecedent implies this term schema in the consequent. So to do that, truth value analysis. So okay, and again, fell swoop applies here. So true. So that gives us true, true, true. And that's true or W and true or F and true. And so that gives us true or W and true or F and true, and that's true, 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 which is true. So here we can see that this premise does imply this conclusion. Yeah. Okay, let me look at the next example. Oh wait, the third example from the book I legitimately cannot fit on a page of writing no matter how far I zoom in. I'm just gonna skip that one. Okay. Give me a second to think up another example. Okay, I think this will work. All right. Okay. I'm actually gonna, we can start the abbreviating a little earlier here. So I'm just gonna set this to not P, this to, that's ugly, Q, and then this to R. And then if we make our conditional to test for implication, whether or not these premises imply this conclusion, we get right, and then the conversion to conjunctive normal form. Again, a lot of these really aren't that bad. Gives us, or I don't know why I'm branching there. So that's, and then double negations cancel out. Okay, so this is actually an example where we don't have to make an existential conditional. So what we're going to do here is we can't do anything more here. This is in CNF, so we plug back in our schemata. So that gives us, oops. Or E, oops. Again, it's really easy to drop a negation sign somewhere, so just try to pay attention as much as you can. It's a mistake that I make, though. Oh, wait, these should be capital letters. Sorry. Okay. And I'm actually going to do one thing. We have rules for eliminating negating conditionals, and it just makes the truth value analysis a little bit shorter. You don't have to do what I'm about to do, but I'm doing it because I know it'll make the truth value analysis shorter. So that's going to give us EP not Q or and then this last one we can't really do anything to that's useful. Okay. And all I did there was use, like, we can still apply all of our rules to something like this. All of the equivalency laws still apply 100%. So then the last thing I'm going to do here is I factor out the E, right? So that gives us and this is just a single Boolean existence schema. And if you remember way back up here, our first law, a Boolean existence schema is valid if and only if its term schema is valid. So going down, right, so what we do to test this Boolean existence schema for validity is we just test the term schema for validity using truth value analysis. PQR. So this might end up being a little long, we'll see. So I'm just going to start with P, no particular reason. So that's true. R, and then false, not Q, or false. Maybe this won't take that long. We'll see. Okay, the left side's going to take a little longer. I'm going to do 2 steps at once, just, again, to save space. So we need to branch again here. So that's going to pick Q, although again, it doesn't really matter. So that's false or true R or R, and that's true or R. So this gives us not R or R, which is obviously valid, and this goes right to true. So on the right side, start reducing. So that gives us false or R or true, and then true. Okay, so we've tested the term schema, and because the truth value analysis always ends in true, the Boolean existence schema here is valid. We got this through converting our premises and conclusion to conjunctive normal form. So the premises here do in fact imply the conclusion. And so this video has gotten like horrendously long, so I'm going to break it off there. I will definitely post some more examples of this throughout the week. I give you guys pretty easy ones in the official videos, and then I get bored and I want to see how hard this stuff actually is if you apply it to really hard stuff. So they'll probably be a little more complicated than this. I'll try to annotate them too. So there aren't that many of these. You only have to do 2, I think, exercises in the chapter. So please try both of these and do your best. I didn't give you hard ones. I just want you to get the method down. And very important, I know that some of you aren't looking at the textbook. I'm going to post this as a rule sheet, but if you look on page 89 of the textbook, I give you the CNF algorithm. So it tells you exactly what to do at every single step. Okay? So check that out if you're confused, and come to my office hours, come to the office hours of the TAs if you're confused, but this isn't as scary as it seems, and good luck with it. Again, if there are any, if anyone's seriously lost, just doesn't know what's going on, please let me know as soon as possible. I'm more than happy to help you. Okay, see y'all next week.